Welcome to meeting 4, part 2. We'll continue to talk about Maria simulator. So in this part, we'll talk about the Maria simulator. We'll give you an introduction. What is the architecture of that machine? We'll talk about the registers and buses used in Maria simulator and the instruction set architecture of Maria simulator. Also, we will talk about the register transfer notation. We are now familiar with computer components, but how these components are connected together, how they work together. There is a saying by Leonardo da Vinci. He said, "When you wish to produce a result by means of an instrument, do not allow yourself to complicate it." So if I want to get a result by an instrument or a machine, I shouldn't make it a complicated machine or a complicated instrument if I want a good result. In this part, we will use Maria. Maria stands for a machine architecture that is really intuitive and easy. So it's a very simple architecture. It has a very simple architecture, and the instruction set of Maria simulator is presented to allow you to gain a full understanding of the basic architectural organization involved in programming execution. Also, Maria exhibits the classical von Neumann design. We have talked about the von Neumann design in part 1 of meeting 4. So it uses the same design and includes a program counter, a register for program counter, also the accumulator as a register. It has also an instruction register. The memory size is 4096 bytes and 2 addressing modes. Assembly language programming is introduced in this part, so we'll talk about assembly language programming to reinforce the concept of instructions format, instruction mode, data format, and control that are presented earlier. This is the architecture of Maria simulator. It's similar to the von Neumann architecture. We have the main memory and the CPU. Inside the CPU, we have the arithmetic logic unit, the control unit. Inside the control unit, we have 2 special registers. As you can see, we have how many registers inside Maria simulator CPU? We have 7 different registers. Each register have a specific job: program counter, instruction register, memory buffer register, memory address register, input register, output register, and the accumulator. We will talk about each one of them in detail through the lecture. The Maria architecture has the following characteristic: binary 2 complement data representation, 2's complement data representation, stored program, fixed word length data and instructions, 4K by 16 word addressable main memory. So it's the memory starts from 0 until 4095. 16-bit instruction. This is important, 16-bit instruction. So each instruction, the size of each instruction is 16-bit. 4 bits of that instruction is, we call it the opcode, which means what kind of instruction are we doing? Is it add? Is it multiplication? Is it store? Is it load? This is the opcode. It's assigned for it is 4 bits. The rest of the 16 bits, which is the 12 bits, remaining 12 bits, are reserved for the address, and we will talk about this in more detail later on. The ALU is a 16-bit arithmetic logic unit, and we have, as I said earlier, 7 registers for control and data movement. The registers in Maria simulator, in general, registers are storage location within the CPU. Yani they are memory places to store data inside the CPU. The ALU portion of the CPU perform all the processing as usual. Arithmetic logic unit do all the arithmetic and logical decisions, arithmetic operation and logical decision. The 7 registers are used for a very specific purpose when the program is executed. What are the 7 registers in Maria? First, AC. AC stands for accumulator. It's a 16-bit register that holds a conditional operator, less than, or one operand of two operand instruction. Usually this register is used to store information that we want to use in a calculation. It's used by the programmer to store data, to load data, and so on. Then we have memory address register, MAR, memory address register. It's a 12-bit register that holds the memory address of an instruction or an operand of an instruction. Memory address instruction or register, it's a memory place that is reserved only for memory addresses, to store memory addresses. Whether this memory address we want to use it to store information in the memory, or we want to use this memory address to get information from the memory. So this register is specially designed for memory addresses. MBR, memory buffer register, it's a 16-bit register that holds data after it's retrieved from or before its placement in memory. Again, memory buffer register is also related or concerned with the memory, related to the memory. Any data that we want to store in the memory, we have first to put it in the buffer, memory buffer register, then it's moved from there to the memory or the RAM. Any data we want to get from the RAM or from the main memory, we have to first get it from the memory and store it in the buffer. From the buffer, we can move it to any other register later on. So memory address register and the memory buffer register, they work closely with the memory. One is for storing the addresses that we are dealing with in the memory, and one for storing data that we want to store in the memory or we want to get from the memory. The next register is PC, program counter. It's a 12-bit register that holds the address of the next program instruction to be executed. So the program counter holds the memory address of our next instruction. Where is our next instruction? Where is it stored in the memory? The memory address is stored in the program counter. Next is the IR, instruction register. It's a 16-bit register that holds an instruction immediately preceding its execution. So the IR is the instruction register. Any instruction that we are executing currently is stored in the instruction register. Any instruction we want to execute later on, we get it from the memory and put it in the instruction register. Next is the in register or the input register. It's an 8-bit register that holds data read from the input device or any input device. So if we enter anything through a keyboard, anything we enter it is stored immediately in the in register or the input register. The last register is the out register, which is also called the output register. Also, it's an 8-bit register that holds data that is ready for output device. So anything we want to, for example, to show on the screen, we want to output on the screen, we will put it will be stored on the output register. What about the buses in Maria simulator? Maria cannot transfer data or instruction into or out of registers without a bus. Of course, we have to use a bus to transfer data between registers, different parts of the computer. In Maria, we assume a common bus scheme. So we have one bus that transfers data between all the parts of the Maria simulator. The registers are interconnected. They are also connected with main memory through a common data bus or the common data bus. And we have a unique number that is set on control lines whenever that device is required to carry out an operation identified each device on a bus. So we'll see in the figure, we have separate connection also. So we have the common bus. This is the common bus, as you can see. Okay. So this common bus connects all the registers and all the main memory and all the parts of the CPU together. So we can, if you want to send from the main memory to the instruction register, we can send it through the common bus and it will go here to the instruction register. But in addition to the common bus, we have separate connection which is provided between the accumulator and the memory buffer. This is a separate bus only between accumulator and buffer. We can send and receive data between them. We have also a separate bus or a connection between accumulator with arithmetic logic unit. We can send and receive data. Also there is a one between the buffer and the arithmetic logic unit. We can also see that we have one between memory address register and the main memory. The data path in Maria is shown in this figure. Note that the data word, that is an instruction in the main memory, travels a relatively long path before achieving the instruction register. As you can see, if we want to send anything from the instruction from the main memory, if you want to save it in the instruction register, it will travel a long way. Maria has a very simple yet powerful instruction set. So now we'll talk about the instruction set of Maria. Instruction set architecture. What are the commands available in Maria simulator, and what can they do? The instruction set architecture, or in abbreviation we say ISA, specifies the format of its instruction and the primitive operations that the machine can perform. The ISA is an interface between computer hardware and software. The ISA, or the instruction set architecture, it tells us what kind of operation this computer can do. It connects the hardware of the computer with the software of the computer. Some ISAs include hundreds of different instructions for processing data and controlling program execution. For Maria, each instruction consists of 16 bits. So now we will talk about the instruction. Any instruction in Maria has 16 bits. These bits are organized as follows. First, we have the opcode. The opcode is the size of the opcode is 4 bits, which is from bit number 12 to bit number 15. It specifies the instructions to be executed, which allow for total of 2 to the power 4. We have 4 bits, so how many instructions can we have? 2 to the power 4, we can have 16 instructions. In Maria, we use only 13. We have only 13 instructions in our instruction set. So again, the first part of the instruction, which has 16 bits, is 4 bits related to the opcode. It tells us what kind of command we are executing now. The next part is the address. The address consists of 12 bits, which are the bits from 0 until 11. It forms the address. So if we have an instruction that has 16 bits from 0 until 15, the first 12 bits from 0 to 11 is the address, and the next 4 bits from 12 to 15 is the opcode. The opcode, the instruction or the instruction sets are, we have here, we'll first discuss, we said that we have in Maria simulator 13 instructions. At the beginning, we'll discuss those 9 instructions, then later on we will add the remaining 4 instructions. This is the binary code of the instruction, which is also the opcode. We call it the opcode as well, to differentiate between a different instruction. So number 1 represent the instruction load. So number 1, or opcode number 1, these are the 4 bits. It means load X. What's load X? Load the contents of address X into AC, the accumulator. So whatever stored in the memory address number X, we will get it and we will store it in the accumulator register. Number 2, which has this opcode in binary, it's store X. Store the content of accumulator at address X. So whatever is there in the accumulator register, we will store it in memory. Where in memory? Memory address number that has the address X. X should be a number. but for simplicity we are using this letter X. Opcode number 3 or instruction number 3, this is the binary code, add X, add X. So what's add X? Add the contents of address X to the accumulator. So whatever stored in address X in the memory, we will get it and we will add it to the content of the accumulator, and the result will be stored in the accumulator. We'll talk about all of these instructions step by step in the next slides. We just want to introduce them now. So instruction number 4, this is the binary code for it, subtract X. So what does that mean? Subtract the contents of address X from AC, from the accumulator. So accumulator, the content of the accumulator, minus the content of address X from memory. Instruction number 5, this is the binary code of 5. It's input. Input means any value, we get it from the keyboard and we put it into the accumulator. So input, any value we got from the keyboard, we put it in the accumulator register. Instruction number 6, output. Output the value in the accumulator to the display. So whatever we have in the accumulator will be displayed on the screen. Instruction number 7, this is the binary code of 7, is halt. Halt means terminate the program, end the program, terminate the program. Just end that program. Instruction number 8, skip condition. Skip condition or skip cond, which means skip condition. Skip next instruction on condition. So using this, we will discuss it in more detail. Skip condition, we have a condition that we need to check. If that condition is true, we will skip the next instruction and we'll go to the instruction after that. If not, then we're not going to skip. If it's false, the condition is false, we're not going to skip the next instruction. We'll just continue as normal in sequential order. Instruction number 9, jump X, which means load the value of X into PC. So our next instruction will be stored in X. We'll change the value of the program counter to the value of X. And we will execute whatever instruction that is stored in this memory location. This table you have to memorize. You have to memorize the numbers, you have to memorize the instruction and the number of each instruction and what does it do. This is an example that we are going to we'll try to understand what's happening inside the Maria simulator when we execute each of these instructions. So the initial value will be in the accumulator. We have the accumulator register, we have the value 5. X is somewhere in memory called X, it has the value 10. Y, also a variable that has a value 2. Z has the value 0. Input and output, this is what is inputted by the keyboard and this is the screen, what will be outputted on screen. So we'll start. So these are the initial value as you can see. So we'll start with load X. Load X means, if you remember, this is instruction number 1. Load X means to get whatever value stored in memory location number X and put it in the accumulator. So what is stored in X? It's 10. So 10 will be stored in the accumulator. This is what load X does. Okay, let's move on to the next instruction. Store Y. Store Y, what does it do? Store Y means whatever in the accumulator, we have to store it in memory location Y. So what is in the accumulator? We have the value 10. So we'll store 10 in Y. So Y will change from 2 to 10, as you can see. Okay, what is our next instruction? Instruction number 3, it's add X. Add X. Add X, if you go back to the table, add X means get the value stored in X and add it to the accumulator and store the result in accumulator. So what is in X? 10. What is in the accumulator? 10. We add 10 plus 10, it's 20, and we store it in the accumulator. Accumulator will change from 10 to 20. The next instruction number 4, is subtract y. So we will subtract whatever in y, we'll subtract it from the accumulator. Accumulator has the value 20, y has the value 10. 20 minus 10 is 10. So this is the new value of the accumulator. Now, we'll move to the next instruction number 5, input. Input, we will get whatever we got in the input from the keyboard, and we will store it in the accumulator. So whatever we get from the input, we'll put it in the accumulator. So now the value of the accumulator is 3. Instruction number 8, I guess. I think they're not in order, but skip condition 800. Okay, skip condition 800. 800 means in this situation, and we will talk about this in detail, 800 means that we're checking whether the accumulator is greater than 0 or not. If it's greater than 0, if it's true, we'll skip the next instruction. We will skip this instruction, jump to finish. If it's false, we will not skip it. Okay, so we will check. Is the accumulator greater than 0? The value there greater than 0? Yes, it's greater than 0. So we're going to skip the jump finish. We're going to store z. We will skip this instruction and we will go to store z. Type. Before we go to store z, what does jump finish means? Jump finish means that we need to go, next instruction would be is stored in or it's the next instruction won't be this, it will be finish. Finish is here, so it will be output. So if this was false, then we will have to do this next instruction and go to finish and output, and we'll ignore these 2 steps. But since the skip condition is true, we will skip the next instruction. We will not do this. We will do store z. Store z means that whatever we have in the accumulator, we have to store it in memory address z, in z. So what we have in accumulator 3, we will store it in z, as you can see here. Then next instruction is add y. So whatever we have in y, we will add it to the accumulator. Accumulator has a value 3. We will add 10 to it. So now the accumulator is equal to 13. And now next instruction is output. We will ignore this. This is just a naming. It's just like a variable or a name or a tag. We can call it a tag. We'll talk about this in more detail later. So output means whatever in the accumulator we'll put it on the display, on the output, on the display. So 13 will be outputted here. And then halt means that this is the end of the program. To understand how things work, let us examine the instruction format used in Maria. So suppose that we have the following 16-bit instruction. So suppose this is our instruction. This binary numbers 16 bits that has 16 bits is our instruction. So if we want to understand this instruction, we have to divide our 16-bit into 4 and 12. So the first 12 bits are the address, and next 4 bits are the opcode. Opcode in binary, this is number 1. Number 1 means load, so it's load. And the address here, if you try to convert this binary number into a hexadecimal number, the first 4 bits here are 7, next 4 bits are 0, and the next 4 bits are 0. So load 007, which means go to memory address 7, get the data there and put it in the accumulator. So the leftmost 4 bits indicate the opcode in red, or the instruction to be executed. So 0001 binary is 1. which represent the load instruction. The remaining 12 bits indicate the address of the value that are loading. So where are we getting the value from? From 007 or the address 7 in the main memory. This instruction caused the data found in address 7 in main memory to be copied into the accumulator register. Note that the value of the address 7 in main memory remains there. So if we take a copy of it, it means we're taking the data in memory address 7, we're just taking a copy of it. We're not removing it. So we're just taking a copy of it and it will remain in the main memory. Okay. However, any previous data found in the accumulator will be overwritten when we use the load instruction. So when we get this data and put it in the accumulator, whatever in the accumulator will be overwritten to put the new data. Let us have another example. Suppose that we have the following 16-bit instruction. So again, we have this 16-bit. The first, these 4 bits, they are the opcode. This is 3 in binary. So if we convert this from binary to decimal or to hexadecimal, it's 3. 3 means add. So the opcode here or the instruction is add. The address, this is it's equal to 14, which is E in hexadecimal. The next 4 numbers is 0 and the next 4 bits are equivalent to 0 in hexadecimal. So the leftmost 4 bits 0011 are equal to 3, which is the add instruction. The address bits indicate 00E in hex or 14 in decimal. We can say 14 in decimal. This means that the order we will be given to go to the main memory, get the data. So we will get the data from the address 00E, and whatever data is found there, we will add it to the value stored in the accumulator register. The new value in the accumulator would then be the sum of the old value of the accumulator plus the value or the data fetched from the address 00E. One important instruction is the skip cond or skip condition. When the skip cond instruction is executed, the value stored in the accumulator must be inspected. So the skip condition is depending on the accumulator, or the condition is related to the accumulator. We have to check the value in the accumulator. The next instruction is skipped if the condition tested true. If the next instruction is not skipped, then the condition tested false. So we will check the accumulator. If our condition is true, if the condition tested true, we will skip the next instruction. If it's false, then we will not skip the next instruction. We need to focus on bits number 10 and number 11 from our instruction, from our address. We have the instruction bits, the 16 bits of the instruction. We will check bit number 10 and bit number 11. If bit number 10 and 11 are 0, 0, it means that we are testing if the accumulator is less than 0. If bit number 10 and 11 from the instruction address is 1, 0, then what is our test? What is the condition? We're checking whether accumulator is equal to 0. If bit number 10 and 11 are 0, 1, then the CPU is testing whether the accumulator value is greater than 0. To make it more clearer, this is an example. So we have a skip condition instruction. Skip condition is number 8. So the opcode for it is 8, which means skip condition. From the address part, the 12 bits of the address parts, we need to focus on bit number 10 and bit number 11. So if bit number 10 is 1 and this is 0, which means in no, we are checking whether the AC or the accumulator value is equal to 0. We call the skip condition 400. Skip condition 400. How did we calculate this? First 4 bits 0, second 4 bits are 0, so this is 0. Last 4 bits, if you transfer them from binary to hex, it's 4. So skip condition 400. We will set that the opcode is 8. Then bit 10 and 11 are 1, 0, which meaning that the next instruction will be skipped if the value of the accumulator is equal to 0. So our condition, if the value of the accumulator is equal to 0. If it's true, we will skip the next condition. If it's not, then we will not skip the next condition. We have different kinds of skip condition depending on the value of the bits 0 and bits 10 and 11. Skip condition 0, 0, 0, it means skip the next instruction if the accumulator is less than 0. This is when both 10 and 11 bit 10 are 0, 0. Skip condition 400, which means skip next instruction if the accumulator is equal to 0. So the condition whether the accumulator is equal to 0. If it's true, we'll skip next instruction. If it's not, we will not skip it. 400, how do we get it? If bit number 10 is 1 and bit number 11 is 0. Skip condition 800, which means skip the next instruction if the accumulator is greater than 0. So if the accumulator greater than 0, we'll skip the next instruction. If not, we will not skip the next instruction. 800, how did we get it? If bit number 10 was 0 and bit number 11 was 1, then we will get this instruction, skip condition 800. To make it more clear, so this is the opcode, number 8, and this is the address. Okay, so the opcode number 8 is skip condition. The first 4 zeros give me the number 0. If you want to try to get the equivalent number in hexadecimal from binary to convert from binary to hexadecimal, we will divide our 12 bits into 4 bits, 4 bits, 4 bits, and then each number we're going to get the equivalent decimal number to it, or hexadecimal number. So 4 zeros is are equivalent to 0. Next 4 zeros are also equivalent to 0. And the last 4 bits are equivalent to 8. So we have the instruction skip condition 800. Skip condition 800, which means that our condition, whether the accumulator is greater than 0. If it's true, we will skip the next instruction. If it's false, we're not going to skip the next instruction. Okay. Next example, also we have opcode, skip condition. First 4 bits are 0, second 4 bits are also 0. Last 4 bits of the address are equivalent to 4, which give us skip condition 400. It means whether you're checking whether the accumulator is equal to 0. This is our condition. If it's true, we'll skip the next instruction. If it's false, we're not going to skip the next instruction. We'll continue as normal. The last example, also we have skip condition as an opcode. First 4 bits from the address 0, second 4 bits of the address 0, and last 4 bits of the address are also 0, which will give us skip condition 0, 0, 0. So the condition for that, what is our condition that we're checking? Whether the accumulator value is less than 0. If it's true, we'll skip the next instruction. If it's not, we'll continue as usual. Maria instruction appears to be very simplistic. So the component level, each instruction involves multiple operations called micro operation. We also call it the register transfer language, register transfer notation. Specifies the exact sequence of micro operations that are carried out by an instruction. So the instruction that we have talked about and the instructions that we have talked about them in a general way, or a very simple way. But if we want to go into more details, how all the registers are used to do all these operations, like load or store or add or subtract, we need to use this micro operation or the register transfer language. In Maria register transfer language, we will use the following notation: M of X, which means the actual data value stored in memory location X. So go to the memory to location X and get the data that is stored there. And we have the arrow notation that indicate the transfer of byte to a register or memory location, which means transferring of data from one register to another or from memory place to another to register and so on. We will represent the RTL for each of the instruction in the instruction set architecture for Maria. So for each instruction in the Maria instruction set architecture, we will give the full register transfer language or notation for it. We'll start with load X. Load X means get the value from the memory location X and put it into the accumulator. This is the simple understanding, but how it actually happens inside the Maria simulator, it actually needs few steps. It's not only one step. So first we need to get the value of X, which is the actual address, and store it in the memory address register. So remember that we said that the memory address register and the memory buffer register are the registers that are concerned with dealing with the memory. So if you want to get anything from the memory, you have to put the address in the memory address register of that memory location. And if you want to get anything from the memory, you have to first put it in the buffer before you transfer it to any other register inside the CPU. And vice versa. If you want to move data from CPU or the CPU registers to the memory, first you need to specify the memory address and put it in the memory address register. And whatever data you want to move there, you have to first put it in the buffer. So the first step to load X, to get the value from memory address X and put it in the accumulator, first you need to put the address X in the memory address register. Then you need to get whatever stored in that memory address in the memory. Okay, so we'll go to the memory in address X, or the address stored in the memory address register. We will get the value that is stored there and we will put it in the memory buffer register. Again, so we'll get the data stored in the memory. Where in the memory? In this address, which is address X. We put it in the memory address register. Okay, so the address stored in memory address register will go to the memory to data address, get the data, and then we move this data to the memory buffer register. From there, from the memory buffer register, we will move the data, the content, to the accumulator. Okay, to the accumulator register. And now we have fulfilled the load X instruction. What about the store X? It's something similar, but in reverse. So store X means get the value from the accumulator and store it in memory in location X. Okay. So first, again, we need to place memory address X, or the address X, in memory address register, because we want to store in that memory address. Then, whatever in the accumulator, we need to move it to the buffer. Okay. Then from the buffer, we'll move the data to the memory. Where in the memory? We will indicate that by the address stored in memory address register. So place the content of the MBR in the memory location MAR in the memory. Okay. Now we'll take an example to explain this in more detail. So, for example, instead of load X, we'll say load 98. So our memory address is 98. This is our memory, and this is the Maria computer CPU. Inside CPU, I just put 3 registers. We know that we have 7 registers, but I just used 3 registers to make it clearer for you. These are the registers that we are going to use in this instruction, load 98. Okay, again, so load 98, instead of X, I specified 98 as the address. This is the memory. These are my memory addresses starting from 0. And these are the contents, what is stored inside the memory location. This is the Maria computer CPU. We have 3 registers that we are going to use in this instruction. So this is the accumulator, this is a memory address register, and this is the memory buffer register. Load 98 means load the content of memory location 98 into the accumulator. What do we have in 98? We have a content 10. So this 10 should move to the accumulator, but it's not done that simply. We have to follow the steps. So first, 98 will be stored in memory address register. Okay. And after that, we need to get the contents of the memory 98 from the memory in address MAR and move it to the buffer. So we'll get the 10 and we'll move it to the buffer. So we have the value 10 in the buffer. The next step is move the value contents of the memory buffer to the accumulator. So we'll move them to the accumulator. And this is how the load instruction is done. Let's move on to the store instruction. So again, we'll say instead of X, we'll have store 98. So whatever in the accumulator, contents of the accumulator, we need to put them in memory location 98. So what do we have in the accumulator? We have the value 55. We need to store it here. We have this 55. We need to store it here in memory location 98. So first we put 98 in memory address register. Then we get the contents of the accumulator. We move them because we want to move them to the memory. We first have to put them in the buffer. So 55 is moved to the buffer. And now from the buffer we have to move it to the memory. Where? In memory location 98, which is stored in the memory address register. So we'll store 55 here. What about add X? Add X means get the value stored in address X and add it to the accumulator. So we will get whatever stored in address X and we will add it to the value stored in the accumulator. So first, the X, which is the address, we'll store it in the memory address buffer. Then we'll get the content from the memory of address MAR and we will store it in the memory buffer register. Then whatever we have in the buffer, we'll add it to the accumulator and the result will be stored in the accumulator. Same with subtract X. So whatever stored in address X will be subtracted from the accumulator. It's actually almost the same steps. So first, X will be stored in memory address register. Whatever in that memory location will be stored in memory buffer register. And then we will subtract accumulator minus memory buffer register and the result will be stored in the accumulator. This is an example of add. So for example, if we said add 2, this is the main memory again, and this is the Maria computer CPU. We have accumulator, memory address register, and memory buffer register. So if we decided to add 2 means go to the memory address 2, get whatever is there, and add the value to the accumulator. So what do we have in memory address 2? 20. 20 has to be added to the accumulator. So the answer should be 75. Let's see how it's done. First, we need to put the address in memory address register. The address is 2. We'll store it in memory address register. Then we'll get whatever in the content in the memory address register in that address, number 2. We'll move it to the buffer. So the value 20 will be moved to the buffer. Then we will add what contents of the memory buffer to the accumulator. And the result is 75, so we will put this in the accumulator, which will change to 75. It's something similar with the subtraction, so I'm not going to give an example of subtraction because it's exactly the same. Instead of addition, we'll do subtraction. What about input? Input a value from the keyboard into accumulator. So how do we get that? We get it from the in register or the input register. So whatever in the input register, it contains the input, will be moved to the accumulator. It's only one step. What about output? same thing, output the value in accumulator to the display. So whatever we have in the accumulator, we'll put it in the output register. So place the content of accumulator that contains the output in the output register to send the data to the display. From the output register, we will send it to the display. Hold, no need for any RTL because it terminates the program. Nothing is done. We have no register transfer notation or language for that. Jump X, it's unconditional branch to given to address X. So we will move to the next instruction will be stored in memory address X. So a program counter is a register that holds the next instruction. Where is it stored? So we'll get X and we'll store it in program counter. So our next instruction will be stored in memory location number X. So load X into program counter. What about skip condition? Okay, this is a little bit complicated. We'll take it step by step. So if instruction register bit number 10 and bit number 11 are equal to 0, 0, then what does that mean? It means that both are zeros. It's skip condition 0, 0, 0, if you remember. It means that we are this is our condition that we're checking. If the accumulator content are less than 0. If this is true, we will add 1 to program counter and store it in program counter, which means we will skip the next instruction. So instead of going to the next instruction 12, it will be 30 instead, for example. So else, if instruction register, bits of instruction register number 10 and 11 are 1, 0, which means that this is skip condition 400, our condition is going to be if accumulator is equal to 0. If this is true, we will add 1 to program counter and store it in program counter. So we will skip the next instruction. If it's false, we'll not do anything. Next, else if the instruction register bit number 10 and 11 are equal to 0, 1, which means that this is skip condition 800. Our condition is going to be if accumulator greater than 0. If this is true, we will add 1 to program counter. If it's not, we'll do nothing. We'll just continue with our program and keep program counter as it is. Okay, machine cycle. It is worth mentioning that Maria, like any other computer architecture, follows the basic machine cycle, the fetch, decode, and execute cycle. We have talked about this in the first part. The fetch, decode, execute cycle is the series of steps that a computer carries out when it runs a program. We first have to fetch the instruction from the memory and place it into the instruction register. So this is the fetch part. Once the instruction register is decoded, this is the decode part, to determine whether it needs to be done next. If a memory value operand is involved, we will have to get it from the memory and put it in the memory buffer register. So if we need any data, we need to get it from the memory and put it in the memory buffer register. So this is the decode part, and with everything in place, the instruction is executed. So we execute the instruction at the end.